Hello. So today I'm gonna take a break from vectors, kind of, and talk about multivariable functions because this is multivariable calculus. So the first thing that I want to talk about is how to take a limit of a certain function. So let's say we have this limit. So x and y. As x and y approaches 0, what will the limit? What is the limit? So we can verify this by doing straight substitution. So you can see here that if we try straight substitution, we're going to have 9 over 0, which is equal to infinity. Which shows that this is that means this is like almost infinity, right? But another way to show this is by saying that the limit as x and y, as this approaches 0 and itself, so just the y-axis, just the y-axis, so we can substitute it. So now we can do substitution. So the x's will become zeros and the y's will become y, right? So we have 9 over 5 y squared. And then that's the solution, right? But we gotta check the other side. We gotta check another line. So remember, with single variable calculus, we just have to check one spot, but now you can come in many different directions. So I came from when x is equal to 0, right, from the y-axis. But now let's come from another way. So what about when x is equal to y? The line x equal to y. So if we approach it this way, so we can write as the limit as x and y as they approach x and x, right? So we have two x's. We can substitute it, so we have 2x squared plus 5x squared. And then this can be simplified to 1 over 7x squared. And there's an issue because we came into this line from different points, right? But they all don't correspond. So what does that mean? That means this limit does not exist. So it looks like there is some type of, yes, it looks like that there is some type of vertical movement, right? But we proved coming from a different line that the limit does not exist. Okay. And now we can move from that. Oh, sorry, that's the any. Okay, so now overall, that's how you take the limits, and in some functions you can just substitute it in and get a certain answer, and or maybe it might just be a simplification factor, and you just need to simplify to get the limit. Another thing that I want to say, you cannot do L'Hopital's in the multivariable thing. That's only on single variable. So now let's talk about derivatives. So the same rule applies to derivatives, except we do it one variable at a time. So we have a function, right? And we are taking the derivative in respect to the function that we want to take it. So to the variable that we want to take it. So let's say we want to take in respect to x instead of y. We can treat y as a constant. and then vice versa. We can take the derivative respect to y and keep x as a constant. So to do this, we can use this example. So to denote a partial derivatives, they're called partial derivatives because you're not deriving the whole thing. So you have to do one thing at a time. So is this little symbol with the function that you're taking the derivative of with the little symbol and respect to whatever you're doing it. So in here, so the partial derivative of in respects to y, to the x, we keep y as a constant, so it's just gonna be 25 x to the fourth y to the third plus we can keep, sorry, this is an e. We can keep this 8 as a constant, sorry, this e to the negative y as a constant and just move this. So this would be 40 x to the fourth e to the negative y. And then if we want to take, and that's the answer, and then we want to take the partial derivative in respect to y, we can do it too. So we can do, so now if we look at this function, we can take down this 3, keep the x's as constants. So we have 15 x to the fifth y to the second, and then look, if we keep 8x, so we can keep it 8x to the fifth as a constant and take the derivative of e to the negative y, we can this e to the negative y would stay, right? This would become a negative. Okay, so so you're gonna have two derivatives because you have, if you think about it, you're coming from two different sections. You're taking the derivative in the direction of the x-axis and the direction of the y-axis. That's why you have two different types of derivatives. Okay, so you can also take the double derivative. So like for example, if I take the double derivative in respect to, so first respect to x, which we just did. Oh, it is just denoted like this, and then in respect to y. So we already did it respect to x. Now we're gonna do it respect to y. So we're gonna use this function. So we can treat the x as a constant, and we're gonna have 75 x to the fourth y squared, and then we're gonna have negative 40 x to the fourth e to the negative y. And then we can do the same thing for the other one. So we already did respect to y, now let's do it respect to x. So we're gonna have, keep this as we already did this, now we're gonna take it to respect to x. So 5 times 15, that's 75 x to the fourth y to the second. And then to do this to respect to x, so negative 40 x to the fourth e to the negative y. So in here, we came with a conclusion. So if you take the partial derivative and then the partial derivative of the other one, it doesn't matter the order, they're going to come out as the same function, as the same derivative. So we did with respect to y first, then respect to x, we got this one, respect to x, and then respect to y, and then we got the same thing as this one. So those are partial derivatives. So now I want to talk something a little different. So we talked about how I was taking the derivative coming from the x-axis and then coming from the y-axis, right? Or you can actually take the derivative coming from any sort of direction you want. There's only a few things you have to do. So you need a function. So we can come up with a new function. We can say the f of x of y is equal to 5 minus 3x squared minus 1 over 5 y to the third, for example. And let's say we choose a point, right? We choose a point at 1, 2, right? Actually, let's do 1, 3. 1, 3. And then, if they just say, oh, take the partial derivatives of this, well, I guess they're not being very specific, so I guess you'll just do it to the x and the y. But if they say in the direction of a certain something, so what happens if they sent you the direction? So that direction is usually going to come out as a vector. So maybe what about the vector 3 and 5? So this is the direction, because remember, vectors give you direction. So in this direction, what is the derivative of this function at that point? So to do this, what we have to do, we have to turn this function into a vector. How do we do this? Well, it's called a thing. If we apply the del operator, a thing called the del operator, onto the function, now we have a thing called a gradient. And I'll talk about gradients in just a second. But the gradient is going to take the partial derivatives, right? It's going to turn this whole thing into a vector. So a gradient is denoted with an upside down triangle, and then with the function, and then it's denoted as the partial of f with the respect to x, and then the partial of f in respect to y. And then that's what a gradient does. It makes those partial derivatives into a vector. So if we apply this, if we say that the partial derivative of f of x and y, well, all we have to do is do one thing at a time. So the first thing is the x component, of course. So we're going to derive this function in respect to x. So again, we can treat everything else as a constant except the x. So 5 and the y's can go away. So this will be negative 6x. And then the y will become negative 3 over 5 y to the second. That's our gradient. And then I guess I'll talk about it after this. So now we want to do the dot product between the gradient and the vector. So this is the general form. So the gradient of f dotted with the vector is not just the vector, it's the unit vector. Will give us our directional derivative. So let's turn this vector into a unit vector. So remember, we just take the square root of this, so it's b9 plus 25, and then that will be 34, square root of 34. So now we can dot it. So we can say 3 square root of 34, and then 5 square root of 34. So now we're dotting the gradient with a unit vector in a certain direction. Okay, so now we can do the dot product. So this times this, so this will be negative 18x square root of 34, and then this times this. Okay, so it's being negative. It's a 5 here and then a 5 here. That will cancel out. So we're just going to be left with this 3 over square root of 34 y squared. And then that's the function of that direction. And then it's asking us for the point 1, 3. So we can plug this whole thing into here, 1, 3. So anywhere there's x, we plug it in. So we're gonna come up with a solution of negative 18 square root of 34 minus, so this 3 is going to become a 9 times 3 is 27. 27 or square root of 34. If we simplify this, square root of 34, and then this will become 45, negative 45. And that's the value of the tangent of in that certain direction. Another thing that I wanted to talk about the gradient was about two main things, two very important things. And one of those things is very important that you remember it later in the course when you're taking multivariable. So the gradient points to the direction. If you just take the gradient and that's it, it always points to the direction of the steepest point on the graph. So like, we could have like this mountain, and I take this is described by a function, right? And then if we take the gradient of this function, it's going to point to the direction of the steepest ascent. If you take the opposite of this, the steepest descent. So that's the number one. It always points to the steepest place on the graph, on the function. Number two, when you take the gradient, it's always going to be orthogonal to the function in the xy plane. So I could have like right here, and then this thing is in the xy plane. So this is x and this is y, right? So if I take this and if I shine it down, it's gonna always be orthogonal to the function. So it's always gonna be orthogonal to the certain function in the xy plane. It's gonna be a two-dimensional vector. Well, this is a two-dimensional vector that's always gonna point. That's always gonna be orthogonal to the contour lines here. So that's one of the number one things that you need to remember for the later in the course. That's it for this. So now next we'll be going over how to compute absolute values, minimum values, and saddle points. Okay, thank you.